Let me ask you something that might bother you. What if I told you that the most important question ever asked about quantum mechanics was asked by a man everybody says got it wrong? That the person who saw the deepest crack in the foundation of modern physics, who pointed at it and said, look at that, was ignored for 30 years. And that, when the dust finally settled, when someone finally checked, it turned out the crack was real. It was exactly where he said it was. The man was Albert Einstein. And the thing he saw, the thing nobody wanted to deal with, is still there, still unresolved, right now, today. And almost nobody talks about it honestly. By the end of this lecture, you are going to understand what Einstein actually said about quantum mechanics. Not the cartoon version, not God does not play dice, the real argument, and you are going to see why it matters, why it shook the foundations of physics, and why it reveals something about nature so strange that most physicists would rather just not think about it. Let's start somewhere simple. Let's start with a coin. I flip a coin. It lands in my hand. I close my fist. Now, before I open my hand, is the coin heads or tails? You say, well, I don't know. Could be either one. Fine. But you believe it is one or the other, right? It's heads or it's tails. You just don't know which the information exists. It's sitting there in my hand. You're just ignorant of it. That's a perfectly reasonable thing to believe. That's how the world works, as far as you've ever experienced it. Now let me ask you a stranger question. What if I told you that according to quantum mechanics, before you look, the coin is not heads and it is not tails? It's not that you don't know. It's that there is no fact of the matter. The coin is in some kind of ghostly combination of both, and only when you open your hand and look does it snap into one answer. Does that bother you? It should bother you. It bothered Einstein. It bothered him enormously, and the reason it bothered him is not because he was old-fashioned or stubborn. It's because he understood something about that claim that almost everyone else missed. See, here's the thing people get wrong about Einstein and quantum mechanics. They tell you this story. They say Einstein couldn't accept randomness. He wanted a clockwork universe. He said God does not play dice, and that was that. He lost the argument to Niels Bohr, and physics moved on. End of story. That is not what happened. That is a fairy tale, and it does a tremendous disservice to one of the sharpest minds that ever lived. What Einstein actually argued was far more subtle, far more dangerous, and far more interesting than I don't like randomness. Let me tell you what he really said. Einstein had no problem with the mathematics of quantum mechanics. Let's be very clear about that. He helped create it. He's the one who said light comes in packets. He's the one who explained the photoelectric effect. He got the Nobel Prize for quantum physics, not for relativity. So when people say he didn't understand quantum mechanics, that's absurd. He understood it perfectly well. What he questioned was not the math. He questioned what the math was telling us about reality. And there's a crucial difference between those two things. Let me show you. Suppose I have a theory that predicts the weather. It says there's a 70% chance of rain tomorrow. Tomorrow comes and it rains. Great, the theory worked. But now I ask, did it rain because there was genuinely a 70% chance built into nature? Or did it rain because of specific air pressure, specific humidity, specific wind patterns, and my theory just wasn't detailed enough to figure all that out? Was the 70% a fact about the world or a fact about my ignorance? That's the question Einstein asked about quantum mechanics. And it's a perfectly legitimate question. It's maybe the most important question you can ask about any theory. Quantum mechanics tells us that an electron doesn't have a definite position until you measure it. It gives you probabilities. You might find the electron here with 40% probability, over there with 25%, somewhere else with 35%. And the standard story, the one Bohr and Heisenberg promoted, says those probabilities are fundamental. There's nothing deeper. The electron genuinely doesn't have a position. It's not hiding. It's not secretly somewhere and you just can't see it. It literally does not have a definite position until you look. Einstein said, wait a minute, how do you know that? How do you know there isn't some deeper description, some more complete picture where the electron does have a definite position and your theory just can't tell you what it is? That's not an unreasonable question. That's a scientific question. And for a long time, most physicists just shrugged and said, who cares? The predictions work. But Einstein cared. He cared because he wanted to know what was real. And he fought for this point over and over in some of the most dramatic intellectual duels in the history of science. At the Solvay conferences in Brussels, where the greatest physicists in the world would gather, Einstein would show up with a new thought experiment every morning. He'd come down to breakfast, and he'd say to Bohr, consider this. Imagine I have a box with a clock and a shutter, and I release a photon at a precise time, and Bohr would go pale. He'd spend the entire day in a panic, pacing around, talking to everyone, trying to find the flaw. And by the evening, Bohr would have an answer, sometimes a brilliant answer, sometimes a surprising answer. But the debates were fierce, and they were real. The thing that's remarkable is that every single one of Einstein's objections was genuinely deep. These weren't silly mistakes. Bohr had to work hard to answer them. And in some cases, the answers Bohr gave were, frankly, not entirely satisfying. They worked mathematically. But they left a philosophical residue, a feeling that something had been swept under the rug. And there's a wonderful irony in one of these debates. Einstein came up with a thought experiment involving a box of light designed to show you could violate the uncertainty principle. And Bohr refuted it by using Einstein's own general theory of relativity against him. The man who challenged quantum mechanics was defeated by his own greatest achievement. That's the kind of thing that only happens in real life. You couldn't put that in a novel. Nobody would believe it. But Einstein didn't give up. He never gave up, because he wasn't trying to prove quantum mechanics wrong. He was trying to understand what it was really saying. And that's a crucial distinction. Now, you might think this is just philosophy, just two guys arguing about interpretation while the equations do the heavy lifting. But Einstein was cleverer than that. He didn't just argue philosophically. He designed a trap, a logical trap. And in 1935, with his colleagues Boris Podolsky and Nathan Rosen, he sprung it. This is the famous EPR argument, Einstein, Podolsky, and Rosen. And let me tell you, it is one of the most beautiful arguments in the history of physics. Not because of the math. The math is simple. It's beautiful because of the logic. Here's what they did, and I'm going to explain it carefully, step by step, because this is the heart of everything. Imagine you have two particles. Let's call them particle A and particle B. They interact with each other, and then they fly apart. One goes to the left, one goes to the right. They travel very far apart, miles apart, light years apart, if you like. Now, quantum mechanics says these two particles are entangled. That's a word Schrödinger actually coined, not Einstein. But Einstein is the one who saw the implications. What entanglement means is that the quantum description of these two particles is linked. Their properties are correlated in a very specific way. Let me give you a concrete example. Suppose the total spin of the two particles is zero. Spin is a quantum property. Don't worry too much about what it is physically. Just think of it as a kind of internal rotation, like a tiny gyroscope that can point either up or down. If the total spin is zero, that means if particle A is spinning up, particle B must be spinning down, and vice versa. They're always opposite. Always. That's the correlation. Now here's where it gets interesting. According to quantum mechanics, before you measure, neither particle has a definite spin. Particle A is not up and it's not down. It's in that ghostly combination. Same for particle B. Only when you measure one of them does it snap into a definite state. But, and this is the key, the moment you measure particle A and find it spin up, you instantly know that particle B is spin down. Instantly. Even if particle B is on the other side of the galaxy, you didn't touch particle B. You didn't send it a signal. You didn't do anything to it. But now you know its spin with certainty. Einstein looked at this and said, fine. So by measuring particle A over here, I can determine the spin of particle B way over there without disturbing particle B in any way. That means particle B's spin must have been determined all along. It must have been real before I looked, because I didn't do anything to it. I couldn't have created its spin by measuring something else far away. That would mean my measurement sent some kind of instantaneous signal across the universe, faster than light. And nothing travels faster than light. You see what he did? He used quantum mechanics' own predictions to argue that there must be more to the story. If the correlations are real, and you can learn about a distant particle without touching it, then that distant particle must have had a definite state before you measured, which means quantum mechanics, which says it didn't, is incomplete. There are hidden variables, some deeper reality that quantum mechanics doesn't describe. That's the EPR argument. It's not, I don't like randomness. It's a precise logical argument. Either quantum mechanics is incomplete, or measuring one particle instantaneously affects another particle far away. Einstein thought the second option was absurd. He called it spooky action at a distance. So he concluded quantum mechanics must be incomplete. Now wait, let's pause here and make sure everyone is on the same page. Let me say this as simply as I can. Imagine I have two gloves, a left glove and a right glove. I put each in a box without looking. I mail one box to New York and one to Los Angeles. Now I open the box in New York and find a left glove. Instantly, I know the glove in Los Angeles is a right glove. No spookiness, no magic. The gloves were always what they were. I just didn't know until I looked. Einstein said that's what's happening with quantum particles. The spins were always determined. Quantum mechanics just doesn't tell you which is which until you look. Like the gloves. Nothing spooky. And honestly, that sounds perfectly reasonable. That sounds like common sense. And for nearly 30 years, most people thought either Einstein was right or that the question was unanswerable and therefore not worth worrying about. Bohr gave a long, somewhat convoluted reply that many people found hard to follow. And physics moved on. People used quantum mechanics to build transistors and lasers and didn't worry about what it all meant. But here's the thing. Here's the hidden gap. The gap that Einstein saw and everybody missed. His argument rested on an assumption, a very reasonable assumption. An assumption so obvious you might not even notice you're making it. And the assumption was this, that the world is local. What does local mean? It means that what I do here right now does not instantaneously affect something far away. Effects travel. They propagate. If I push a ball, the ball rolls and then hits another ball. The influence travels from one place to the next. It doesn't teleport. That's locality, and it's not just common sense. It's built into the theory of relativity. It's one of the deepest principles Einstein himself discovered. Nothing travels faster than light. Influences propagate at finite speed. Einstein's argument was essentially quantum mechanics is either incomplete or it violates locality. And since locality is sacred, quantum mechanics must be incomplete. And for 30 years, that's where things stood. A stalemate. Nobody could figure out how to break the tie. You had Bohr saying quantum mechanics is complete and you just have to accept it. You had Einstein saying it can't be complete because that would violate locality, and nobody had a way to test who was right. It seemed like pure philosophy until 1964. That's when a quiet Irish physicist named John Bell changed everything. And what he did was extraordinary. He found a way to test Einstein's assumption. He showed that the question wasn't philosophy, it was physics, and it had an answer. Here's what Bell realized. If Einstein is right, if there are hidden variables, if the particles have definite properties all along, like the gloves in the boxes, then the correlations between measurements on the two particles have to obey certain limits. There are specific mathematical inequalities, specific numbers that the correlations cannot exceed. These are called Bell's inequalities. But if quantum mechanics is right, if the particles genuinely don't have definite properties until measured, and they're truly entangled, then the correlations can exceed those limits. Quantum mechanics predicts stronger correlations than any local hidden variable theory allows. Let me say that again because it's crucial. Bell proved a mathematical theorem that says if the world is local, if Einstein is right that there are hidden variables and no spooky action at a distance, then the correlations between measurements on entangled particles are bounded. They can only be so strong. But quantum mechanics predicts they're stronger than that bound. So now you can do an experiment. You set up two entangled particles. You measure their spins at different angles. You compare the correlations, and you check, do they stay within Bell's limit or do they break through it? This was actually done. The most famous experiments were by Alan Aspect in Paris in 1982, though there were earlier ones too, and the results were clear, crystal clear. The correlations broke through Bell's limit. Quantum mechanics was right. Nature violates Bell's inequality. And let me tell you something about those experiments, because the details matter. One of the things Einstein might have said is, well, maybe the particles are communicating somehow. Maybe there's some signal we haven't detected traveling between them. So Aspect designed his experiment to close that loophole. He set it up so that the choice of what to measure on each side was made at the very last instant. So fast that no signal traveling at the speed of light could possibly get from one detector to the other in time to influence the result. And even with this safeguard, the correlations were still there, still exceeding Bell's limit, still matching quantum mechanics perfectly. Later experiments pushed this even further. They put the detectors farther apart. They used random number generators to choose the settings. They even used light from distant quasars, light that had been traveling for billions of years, to make the random choices. The idea being that those photons from ancient quasars couldn't possibly have been influenced by the experiment. And still the correlations held. Still Bell's inequality was violated. Every single time. The experimental verdict is as close to certain as science gets. Whatever's going on, it's not a fluke, it's not an artifact, it's not a loophole, it's real. Now, what does that mean? Let me be very careful here, because this is where people get confused and where all sorts of nonsense gets said. What it means is that at least one of Einstein's assumptions was wrong. Either the particles don't have definite properties before measurement, or measuring one particle does affect the other one instantaneously, or both. The simple glove story doesn't work. The world is stranger than that. Let me explain why the glove analogy breaks. With gloves, no matter what angle I examine them from, a left glove is a left glove. But with quantum particles, Bell showed that the correlations depend on what angle you choose to measure the spins at, and the pattern of correlations across different angles is too strong to be explained by any pre-existing properties. It's as if the gloves could somehow sense what you're about to do and change accordingly. That's not how gloves work, but it is how entangled particles work. Now, does this mean Einstein was simply wrong? Well, yes and no, and this is the part of the story that nobody tells properly. Einstein was wrong about the specific conclusion. There are no local hidden variables. The simple picture of particles carrying definite properties like little name tags doesn't survive. Bell killed that. The experiments confirmed it. On that point, Einstein was wrong. But Einstein was profoundly right about the problem. He identified a real tension in quantum mechanics, a real gap. He showed that quantum mechanics, if it's complete, implies something deeply non-local about reality, something that connects distant parts of the universe in a way that seems almost magical. And that implication is absolutely real. It's been confirmed by experiment. Einstein was the first person to see it clearly, and everyone else either missed it or pretended it wasn't there. That's the irony. Einstein intended the EPR argument as a criticism of quantum mechanics. He meant to show that quantum mechanics was absurd by demonstrating it implied spooky action at a distance. But instead, the experiments showed that spooky action at a distance is real, not in the sense that you can send messages faster than light. You can't. The correlations are there, but they can't be used to transmit information. It's subtler than that. But the non-locality is real. The entanglement is real. And Einstein is the one who discovered it. Let me say that differently for anyone who's getting lost. Einstein, the man everybody says was wrong about quantum mechanics, is the person who discovered quantum entanglement. He discovered it while trying to prove quantum mechanics was flawed. He said, "Look at this absurd consequence." And nature said, "Yes, that's exactly how I work. That's one of the most wonderful twists in the history of science." Now, I want to go deeper, because there's a layer here most people never reach, and it has to do with what we mean by real. Quantum mechanics gives us probabilities, beautifully accurate probabilities, but it doesn't tell us what's happening when we're not looking, and that's the hidden gap. not a gap in the math. The math is perfect, a gap in the story, a gap in our understanding of reality. Let me give you an example. You've got an electron going through a double slit, two tiny openings in a wall. If both slits are open, the electron behaves like a wave. It interferes with itself. You get a pattern of light and dark bands on the screen behind the wall, an interference pattern. But if you put a detector at one of the slits to see which way the electron goes, the interference vanishes. The electron behaves like a particle, goes through one slit or the other. Now, what happened? When you weren't watching, the electron seemed to go through both slits at once, like a wave. When you watched, it picked one. The act of observing changed the outcome. What was the electron doing when no one was looking? Quantum mechanics doesn't say. It cannot say. It gives you a recipe for predicting measurement outcomes, and the recipe works magnificently. But ask, what is the electron doing between measurements? And the theory is silent. That's the gap Einstein was pointing at. Not a mathematical error, a gap in what the theory tells you about reality. And Schrödinger saw the same gap, by the way. This is the guy who invented the wave equation. The fundamental equation of quantum mechanics bears his name. And even he was disturbed by what his own theory implied. That's where the famous cat comes from, Schrödinger's cat. You've heard of it. I'm sure everybody's heard of it. But most people miss the point of it entirely. Here's what Schrödinger was actually saying. Take a radioactive atom. Quantum mechanics says that until you observe it, the atom is in a superposition of decayed and not decayed. Fine, that's weird, but it's an atom. It's small. Maybe small things are allowed to be weird. But now, hook up a detector to the atom. If the atom decays, the detector triggers a hammer, the hammer breaks a vial of poison, and a cat in a sealed box dies. If the atom doesn't decay, the cat lives. According to quantum mechanics, if the atom is in a superposition, and every step of the chain follows the laws of quantum mechanics, then the cat should also be in a superposition, alive and dead at the same time. Not alive or dead, and we don't know which. Alive and dead simultaneously. Schrödinger wasn't proposing this as a real experiment. He was making a point. He was saying, look how absurd this gets when you scale it up from atoms to cats. Somewhere between the atom and the cat, something happens that quantum mechanics doesn't describe. There's a gap. That's the same gap Einstein saw. The two greatest critics of quantum mechanics were pointing at the same blind spot, and it's still blind. We call it the measurement problem. At what point does quantum superposition end and definite reality begin? When does the many become one? When does possibility become fact? Quantum mechanics gives us no answer. It just says, when you measure. But what counts as a measurement? Does the detector measure the atom? Does the cat measure the detector? Do you measure the cat when you open the box? Does the whole room have to be observed by someone outside? You see how this spirals, and it's not silly. It's pointing at something genuinely unresolved. Every interpretation of quantum mechanics is, at bottom, an attempt to answer this question. And none of them answers it without introducing something strange. And there's another thought experiment that makes this even more disturbing. It's called the delayed choice experiment, and it was dreamed up by John Wheeler. Here's the setup. You send a photon toward two slits. Normally, you decide before the photon arrives whether you're going to watch which slit it goes through or whether you're going to let it go through and just look at the pattern on the screen. If you watch, you get particles. If you don't, you get waves. Fine. But Wheeler said, what if you wait? What if you don't decide until after the photon has already passed through the slits? The photon is already on the other side. It's already done whatever it did. And then, at the last instant, you choose. Do I look at which slit, or do I look at the interference pattern? And here's the astonishing thing. Even though the photon has already passed through the slits, your later choice determines what it did. If you choose to check which slit, no interference, the photon went through one slit, like a particle. If you choose to look for interference, there it is. The photon went through both, like a wave. Your decision now seems to reach back in time and determine what the photon did then. Now, I want to be very careful. It doesn't actually violate causality, no information travels backward. But it demolishes the simple picture of a photon that is something definite at every moment, traveling a definite path through one slit or the other. The photon's past is not fixed until you choose how to observe it in the present. Reality, in some sense, is not fully determined until it's observed. That's the gap. That's Einstein's gap made vivid. The theory doesn't just refuse to tell you what's happening between measurements. It seems to suggest that what's happening between measurements depends on what you choose to do later, and that's either deeply profound or deeply troubling, depending on your temperament. And this isn't some minor philosophical quibble. It goes to the heart of what a physical theory is supposed to do. Is physics just about predicting the outcomes of experiments? Or is it about telling us what's really out there, what the world is made of, what's happening when no one is looking? Bohr in the Copenhagen school said, roughly speaking, don't ask. The question is meaningless. There is no reality independent of observation. Einstein said, that's crazy. The moon is there whether or not I look at it. And you know what? I sympathize with Einstein. I really do. Because if physics can't tell us what's real, then what is it for? But here's the uncomfortable truth. After Bell's theorem, after the experiments, we know that any picture of reality we construct has to be very strange. If you want particles to have definite properties at all times, you can do that, but you have to accept non-locality, instant connections between distant particles. David Bohm worked out a theory like that. It's perfectly consistent, gives all the same predictions as quantum mechanics, but it requires this non-local influence. Or you can say particles don't have definite properties until measured, and the act of measurement somehow brings reality into being. That's more or less the Copenhagen view. But then you have to explain what counts as a measurement, and why consciousness or big objects play some special role. And nobody's really done that satisfactorily. Or, and this is another option, you can say the wave function never collapses. Every time a measurement happens, the universe splits. All outcomes occur, each in its own branch. That's the many worlds interpretation. It preserves locality in a sense, but at the cost of an unimaginable inflation of reality. These are the options. These are what we're left with. And none of them is entirely comfortable. That's the honest situation. That's the gap Einstein pointed at, and it's still there. We've learned an enormous amount since Einstein. We've confirmed entanglement. We've tested Bell's inequality to extraordinary precision. We've built quantum computers that exploit these very properties. But we still don't have a consensus on what it all means, on what is really going on. Let me do a thought experiment with you. This is the kind of thing that keeps me up at night. Well, not really up at night. I sleep fine. But it keeps me thinking. Imagine Alice and Bob. They're very far apart. Alice has particle A, Bob has particle B. The particles are entangled. Now, Alice and Bob have agreed beforehand that they're each going to measure their particle's spin, but they get to choose which direction to measure. They can measure spin along the vertical axis, or along some tilted axis, say 30 degrees, or 60 degrees, or whatever they like. They each make their choice independently, they each do their measurement, then they get together later and compare results. Now, if Einstein's hidden variable picture were right, each particle would carry a little instruction set, a cheat sheet. He would say, if they measure me vertically, give them up. If they measure me at 30 degrees, give them down. If it's 60 degrees, give them up. Like a little lookup table, the particle has a definite answer for every possible question, determined in advance. Bell showed that if you work out the statistics, any such lookup table, any such hidden instruction set, limits how correlated Alice's and Bob's results can be. There's a ceiling, and quantum mechanics breaks through that ceiling. The quantum correlations are stronger than any pre-programmed instruction set could produce. Think about what that means. It means the particles cannot be carrying predetermined answers. The correlations are too strong. It's as if somehow the particles are coordinating their answers in real time at the moment of measurement across any distance, not by sending a signal, not by any mechanism we can identify, but coordinating nonetheless. Let's sit with that for a moment, because I think people rush past it. We've gotten used to saying quantum weirdness as if it's just a thing, like bad weather, something you shrug at. But this is genuinely one of the strangest facts ever established about nature. Two objects, separated by any distance you like, are correlated in ways that cannot be explained by any local mechanism. That's been proven mathematically and confirmed experimentally, repeatedly, with increasing precision and rigor over decades. It's as solid as any result in physics, and it doesn't fit into any picture of the world that you've ever been taught. It doesn't fit into Newtonian mechanics. It doesn't fit into everyday experience. It barely fits into general relativity, which is built on the idea that physics is local, that what happens here is determined by what's nearby, not by what's happening on the other side of the universe. There's a wonderful way to put this that I think clarifies the strangeness. In a classical world, if you want to describe a system of two particles, you describe particle 1 and you describe particle 2, and you're done. The state of the pair is just the combination of the individual states. That's how classical physics works. The whole is the sum of the parts. In quantum mechanics, that's not true. The whole is more than the sum of the parts. Two entangled particles have a joint state that contains more information than both individual states combined. And that extra information, that irreducible togetherness, is entanglement. It's not stored in particle A. It's not stored in particle B. It's stored in the relationship between them. It's a new kind of correlation that has no classical counterpart. Nothing in your everyday experience prepares you for it. And Einstein saw it first. He saw it, named it absurd, and tried to use it to argue that quantum mechanics was missing something. He was wrong that it meant the theory was incomplete in his sense. But he was right that it meant something extraordinary about the nature of reality, something we're still grappling with. Now you might say, so what? Weird quantum stuff. Fine. What does it change? It changes everything, because it tells us that the universe is not like a machine where each part operates independently. The parts are connected in a deep, fundamental, non-classical way. And Einstein was the first person to clearly articulate this, even though he intended it as a criticism. Let me tell you another thing that most people don't appreciate. The EPR argument didn't just reveal entanglement. It revealed something about the nature of information in the universe. In classical physics, information is local. The information about what's happening here is here. The information about what's happening there is there. You can, in principle, describe the state of the universe by listing the state of each region independently. Quantum mechanics says no. When particles are entangled, the information about their joint state is not stored in either particle separately, it's stored in their relationship. The whole is not equal to the sum of its parts. You can know everything there is to know about particle A individually, and everything about particle B individually, and still not know everything about the pair. There's information in the correlation that isn't in either piece. That is revolutionary. That's a completely new kind of information, a new kind of reality. And it's the basis for quantum computing, quantum cryptography, quantum teleportation, all of these technologies that are being developed right now. They all rest on this property that Einstein uncovered. Now, let me deal with a misconception, a big one. People hear about entanglement, and they say, oh, so you can communicate faster than light. You can send signals instantly. No, 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 you cannot. Let me explain why. Because this trips up almost everybody. When Alice measures her particle and gets up, she knows Bob will get down. But from Bob's point of view, all he sees is a random result, down. He has no idea whether Alice is measured yet or not. He can't tell from his result alone. His results look completely random. It's only when they compare notes later, through normal channels, traveling at the speed of light or slower, that they can see the correlations, so the correlations are there. The non-locality is there. But it's hidden in a very specific way that prevents you from using it to send a message. Nature is clever. It's as if the universe is saying, I'll be as weird as I want behind the scenes, but I won't let you exploit it to violate causality. It's a very delicate balance. And understanding exactly why this works, why entanglement is real but not usable for communication, is one of the deepest and most beautiful results in quantum information theory. Now let me give you something more concrete about Bell's inequality, because I think it helps to see the numbers. It makes the whole thing feel less abstract and more like the kind of thing you can grab hold of. Suppose Alice and Bob each have a choice of 3 measurement settings. Let's call them settings 1, 2, and 3. They pick randomly, independently, and they each get a result, either plus or minus, up or down. Now, if hidden variables are real, if each particle carries a little instruction set, like I said before, we can work out the statistics. If Alice picks setting 1 and Bob picks setting 2, the instruction set determines whether they get the same result or different results. And if you work through all the possible instruction sets, all the possible cheat sheets the particles could carry, you find that Alice and Bob must agree at least a certain fraction of the time when they happen to pick different settings. Here's the key number. If Einstein's local hidden variables are right, the probability that Alice and Bob get the same result when they choose different settings must be at least 1/3. That's the bound. That's Bell's limit for this particular setup. But quantum mechanics predicts they agree only 1/4 of the time, less than 1/3. That violates the inequality. And when you do the experiment, you get 1/4, not 1/3. Quantum mechanics wins. The hidden variables lose. Now, 1/4 versus 1/3 might not sound like a big deal. It's a difference of about 8 percentage points. But mathematically, it's everything, because it's not within any margin of error. It's a clean, sharp, experimentally testable difference. And it means the entire framework of local hidden variables is wrong. Not slightly wrong. Fundamentally wrong. No local hidden variable theory, no matter how clever, can reproduce the predictions of quantum mechanics. Bell proved that as a mathematical theorem. The experiments confirmed it as a physical fact. And I want to emphasize something. This is not about our current technology being too crude to find the hidden variables. It's not like saying, well, maybe with better instruments we'd find the instruction set. No, Bell's theorem is a mathematical proof. It says no such instruction set exists that can reproduce these correlations. Full stop. It's not a practical limitation. It's a logical impossibility. That's what makes it so devastating. Let me come back to Einstein for a moment, because I want you to understand his position sympathetically. The man was not a fool. He was not clinging to an outdated worldview. He identified a real problem. The problem of reconciling quantum mechanics with locality, with our intuitive understanding of space and separateness. And that problem is not solved. It's papered over. We have interpretations that handle it differently, but none that makes it go away entirely. In the Bohm interpretation, non-locality is explicit. It's built right in. Particles influence each other instantaneously. It gives the right answers, but at the cost of non-locality. In many worlds, there's no collapse and no non-locality in the usual sense, but you get an infinite branching of reality. Is that better? Is that worse? It depends on what bothers you more. In Copenhagen, you're told not to ask about what's real between measurements, and measurement is left vaguely defined, which has always struck me as a bit of a cheat. Like solving a puzzle by declaring the missing piece doesn't exist. And there are newer approaches. Quantum Bayesianism, or Cubeism, says the quantum state is about your beliefs, not about reality. That's interesting, but it sidesteps the question of what's actually out there. The point is, there is no consensus. And the reason there is no consensus is that the problem Einstein identified is genuinely hard. It's not solved, and anyone who tells you it is solved is either oversimplifying or trying to sell you something. You know what I find magnificent about this whole story? It's not the physics. Well, the physics is magnificent too, but it's the human story. Here's Einstein, the greatest physicist of his generation, maybe of any generation, and he spends the last 30 years of his life arguing that quantum mechanics is incomplete. Everyone thinks he's wrong. The younger generation rolls their eyes. Poor old Einstein, stuck in the past. And then, decades later, Bell proves that Einstein's question was the most important question anyone had asked. The experiments confirm that the weirdness Einstein pointed at is real. And the whole field of quantum information, quantum computing, quantum cryptography, all of it traces back to Einstein's stubborn insistence that something was missing. Einstein didn't get the answer he wanted. Nature turned out to be stranger than he hoped, but he asked the right question. And in science, asking the right question is half the battle, maybe more than half. Let me give you one more way to think about this. Imagine you're an architect. You've built a beautiful building. It looks perfect. All the rooms are in the right place. The plumbing works. The electricity works. But somebody comes along and says, hey, I looked at the blueprints and there's a room in this building that has no doors, no windows, you can't get in or out. And the blueprints don't explain what's inside. You say, the building works fine. Every room you can actually enter is perfect. And the other person says, yes, but what's in that sealed room? That sealed room is the gap Einstein found. The room with no doors is what quantum mechanics doesn't tell us about the world between measurements. The building works perfectly for all practical purposes. You can live in it. You can use every room you can access. But there's a sealed chamber at the center, and we don't know what's in it. And Einstein was the one who looked at the blueprints carefully enough to notice it was there. Some physicists say the room is empty. Some say it's full of branching universes. Some say the question is meaningless. Some say we need a whole new building. But nobody denies the room is there. Not anymore. After Bell, after the experiments. Now, let me talk about something that flows from all of this, because it's really quite wonderful. Entanglement isn't just a philosophical curiosity. It's a resource. It's a physical resource like energy or information. Here's something beautiful. If Alice and Bob share entangled particles, they can do something called quantum teleportation. Don't get excited. It's not Star Trek. You don't disappear and reappear somewhere else. What happens is that the exact quantum state of a particle in Alice's lab can be transferred to a particle in Bob's lab using their shared entanglement and a classical communication channel. The state disappears from Alice's particle and appears on Bob's particle. And this works. It's been done experimentally. It's not science fiction. It's real. And it requires entanglement, the very thing Einstein thought was absurd. The spooky action at a distance that he ridiculed is now a practical tool. That's the kind of joke nature plays. Or quantum cryptography. If you use entangled particles to create a secret key between two people, any eavesdropper necessarily disturbs the entanglement. You can detect the spy. It's like having a communication channel that's guaranteed to be secure by the laws of physics, not by the difficulty of some math problem that a clever enough computer might solve. And again, this works. It's been demonstrated. Banks and governments are interested, all because of the phenomenon Einstein pointed at and said, that can't be right. And quantum computing. A quantum computer uses entanglement and superposition to process information in ways that a classical computer cannot, not just faster, fundamentally differently. Certain problems that would take a classical computer longer than the age of the universe to solve could, in principle, be solved by a quantum computer in minutes. And at the heart of this power is entanglement. The very non-local correlations that Einstein found so disturbing. And here's the really wonderful thing. The power of a quantum computer doesn't come from being faster at doing the same thing a classical computer does. It comes from doing something entirely different. A classical computer processes bits, zeros and ones, one at a time or a few at a time. A quantum computer processes qubits, which can be in superpositions of 0 and 1, and which can be entangled with each other. And because of entanglement, when you have, say, 300 qubits, the quantum state lives in a space that is unimaginably large, larger than the number of atoms in the observable universe. That's where the power comes from the entanglement, from the very thing that seemed like a bug in the theory. It's a feature, the biggest feature, and that's something Einstein could never have anticipated, that the spooky action he identified as a flaw would turn out to be, perhaps, the most powerful computational resource nature has to offer. That's not irony. That's poetry. So here we are. Einstein's absurd consequence turned out to be one of the most important features of the natural world. And the gap he identified, the question of what quantum mechanics really tells us about reality, is still wide open. Let me close with what I think is the most important lesson in all of this. Not just about physics, about thinking. Einstein was able to see the gap because he took the theory seriously, more seriously than the people who were using it every day. The people using quantum mechanics were happy that it gave the right predictions. They didn't care about the sealed room. They didn't need to open it. But Einstein said, a theory that doesn't tell me about reality isn't finished. And he was willing to spend decades being wrong, or being thought wrong, because he believed the question mattered. That takes courage. That takes intellectual honesty of a very high order. Because the easy thing to do is what everyone else was doing. Shut up and calculate. The hard thing is to say, I don't care if it works. I want to understand. And that's not stubbornness. That's the deepest kind of scientific integrity there is. Now, I'm a practical man. I love calculations. I love getting the right answer. But I also think understanding matters. And I think Einstein's example teaches us something we desperately need in physics and in every other field. The willingness to say, this works, but I don't understand why, and I'm not going to pretend I do. The quantum truth Einstein saw that everyone missed wasn't about dice or randomness or clinging to the past. It was about the nature of reality itself. It was the recognition that quantum mechanics, our most successful theory, our most precise theory, has a hole at its center, a place where it goes silent, where it refuses to tell us what's happening. And that silence is not nothing. It is a clue that we still haven't fully followed. Maybe someday somebody in this room or somebody listening to this will follow that clue all the way to the end. And when they do, they'll have Einstein to thank for pointing the way. The man who was wrong about the answer, but magnificently right about the question. And I'll confess something. I've been guilty myself. I've said to students, nobody understands quantum mechanics. I've said it almost as a joke. But there's a truth underneath the joke that I don't always unpack. When I say nobody understands it, I mean nobody understands what it's telling us about reality. The math we understand, the predictions we understand, the experiments we understand, but the story, the picture of the world that goes with the equations, that we don't have. And that's not because we're not smart enough. It's because the theory itself doesn't give it to us. That's the gap. That's Einstein's gap. And I sometimes wonder whether physics has developed a bad habit, a habit of being too practical, of saying, if it works, don't worry about what it means. And look, I understand the temptation. The predictions are extraordinary. Quantum electrodynamics, the theory I worked on, agrees with experiment to 10 decimal places. 10 decimal places. It's like predicting the distance from New York to Los Angeles to within the width of a human hair. That's how good the theory is. So when someone comes along and says, but what does it mean it's easy to wave them away? It means we can predict things, you say. What more do you want? But Einstein wanted more. And I think he was right to want more. Because a theory that predicts without explaining is like a map without a territory. It tells you where to go, but not what's there. And sooner or later, you need to know what's there, because that's how you find the next theory. That's how you make progress.